Okay, we talked about matter and atoms and molecules, but now we're really going to look at atoms in detail. So Dalton proposed that all the atoms of a particular element are the same. They have a lot of things that are the same. They have similar chemical and physical properties. And he proposed that they have the same mass. They actually have some variations in mass. So that was not correct, but a lot of the rest of his propositions were. At that point, it was known that there was something that has mass, and it was known that there were negative particles that could be manipulated, moved around. So our initial take on that was this idea of the plum pudding model, where there's this delocalized positive charge with little pieces of negative charge. And then Rutherford went to test that. There we go. This is a really cool experiment because he just took gold, right? Gold is a metal. You can pound it out very thin. And it's widely available. You see in old art that they have like gold leaf over the frame, just applied. So very thin, molecules thick layer of gold. Pounded it out flat, and then they would use an alpha particle emitter. So this is a radioactive element that emits particles. They send it through a column, so they're all going the same direction. And alpha particles have a pretty small mass, but they have a charge of +2. So it's a positive particle. And as these go through this very thin foil, the idea is they should just pass right through, because that model had just that delocalized positive charge and little bits of negative charge. So that's what it might look like. Now that screen around the outside is a phosphorescent screen. So if you remember the old computers with the green display, that's phosphor. So that they just used phosphorus, and when it was hit by a particle, it would glow. So they could measure where that particle hit, and we expected to go straight through the foil. Now, some of the particles would get deflected. They would just go off at a weird angle, and that made no sense. How would that happen? And then some of them would just hit a wall. And again, how could that possibly happen? So with this data, they were looking at this for maybe 10 months or a year before somebody came up with an idea that would explain this. So it seems so obvious in hindsight. We compare the accepted model at the time was like this delocalized positive charge. We'd expect everything to go through. Eventually someone said, well, what if all of that positive charge is in one place? And that would explain the deflection, because those alpha particles are positive, so they get close to the nucleus and they veer away because of the positive repulsion. Then there's another instance where it hits a wall. It's like a wall inside a very thin foil. So why would that happen? The proposal was that maybe there's something that all the mass for each atom is in one location, a very small location, but very dense. And so that gave us the idea of the nucleus. So here are how the observations in those experiments led to the conclusions. And these are the accepted characteristics of the atom now. Atoms are mostly empty space. And in the center, there's a very dense, positively charged particle called the nucleus. So it has all of the mass of the atom in the nucleus and all of the positive charge. It turns out that the negative charge is delocalized. And we'll spend a different chapter talking about electrons. Okay, so putting this together between all of the knowledge at that point, Dalton's atomic theory and Rutherford's nuclear model, we get this tiny dense center with all of the positive charge and all of the mass, and the electrons are out in these shells. on the outside. So here's my picture. Now the nucleus is really small, but inside are the protons. They're positively charged, and the neutrons. So protons and neutrons have mass. It looks small. Talk about that in a minute. And then outside are the electrons, and those are the negatively charged particles. So we have the location for our subatomic particles either in the nucleus or outside of the nucleus. And protons are +1, neutrons are neutral, and electrons are negative in the same amount of charge as the proton. Okay, so I have a joke for you, which I know I'm terrible with jokes. Okay, a neutron walks into a bar, and the bartender says, "For you, no charge." Okay, there we go. All right, the nucleus is very small. And if we look at the distance of the atom, so the diameter of the atom, it's about 10 to the minus 10 meters. It's small. It's so small, it's very hard to conceive of. But then the nucleus is 10 to the minus 15th. So it's 10,000 times smaller. So 5 zeros, 5 orders of magnitude smaller than the atom itself. I like to talk a little bit about our fundamental forces so that you can always be thinking about what is this balance of forces, what's going on. And in this way of thinking about things, you can find all of the mysteries of chemistry that I found very interesting, all of the quantum mechanical mysterious behavior. So in general, opposites attract each other. Positive charge and negative charge want to come together, just like magnets. Maybe you've seen magnets and you can feel them pull together when they're close. When they're far apart, they don't really feel each other. But when they get close, they want to snap together. And if it's the same charge, if you reverse one of the magnets, they repel. So far apart, they don't feel each other, but close together, they won't come closer. You can feel them pushing away. So those are our general electrostatic forces, and we can always be thinking of those. In many cases, they govern a lot of our behavior of molecules. Now, in the nucleus, we get some exceptions. So for example, we're talking about the nucleus of the atom. The protons are all inside this very small distance. Why don't they fly apart? Why don't they repel each other? We don't really know, right? We see that they stay there. We observe it again and again and again. It never changes, but it doesn't make any sense in the electrostatic model. And so how do we handle this? We give it a name. The nuclear strong force holds those protons in the nucleus, right? It's just a force that's stronger than the electrostatics on that very tiny length scale. So when there's a mystery, when we don't understand something, we document how it behaves, we give it a name, and then we move on. We use it, we know it, but we just move on. Nobody really understands exactly how that works, although people study it in, nuclear physics. So that's one of the mysteries. How do those protons stay in a tiny, tiny space when they want to fly apart electrostatically? So we give it a name, we move on. Now we're gonna make a unit substitution. So what I have in the previous slide was the mass of the protons and the neutrons in kilograms, 10 to the minus 27 kilograms. And that is so small, we can't even imagine how small that is. All we can really do is count the zeros, say, okay, that's very small. So we make a unit transformation to atomic mass units. The symbol for that is U, a cursive U. The older symbol is AMU, atomic mass units. So I tend to stick with AMU. because U just seems like maybe it's confusing. Anyway, we won't be working in atomic mass units for long, but this units transformation allows us to go from kilograms to using integer values. So we're going to say that protons and neutrons have a mass of 1 AMU. They're not exactly the same, but our definition splits the difference so that they are the same to 3 significant figures, which is pretty good. They're pretty close. Then electrons, if you remember, maybe I'll add this value here. Electrons had a mass of 9.1 times 10 to the minus 31 kilograms. So 10 to the minus 31 kilograms, it's also very small. It's actually 2,000 times smaller than a proton. So we're going to call it a mass of 0. Electrons have a very tiny mass, but much smaller than protons and neutrons. So when we make the transformation to atomic mass units, the electrons have a mass of 0 effectively. All right, so in an atom, we're going to start out talking about neutral atoms. Atoms can add and remove electrons and form charged particles, but I like to think about that later. I think that's section 4.7, where they're adding and removing electrons. So we're going to look at that in a later section. First, I like to work with neutral atoms. So if it's electrically neutral, that means the plus charges are equal to the negative charges. They cancel out to a neutral atom. So we know for neutral atoms, the number of protons in the nucleus equals the number of electrons in those outer shells. And on the periodic table, we see that the atomic number increases just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the atomic number increases by 1. That corresponds to the number of protons in the nucleus. It's the number of protons in the nucleus that tells us which atom it is. It creates the identity of that atom. So if we look at the periodic table, we have our numbers right up at the top. 1, 2, 3, 4. And then we have our masses down below. We'll talk more about the masses. The two particles that have mass are the protons and the neutrons. And they both live in the nucleus. So when we add those together, that's the mass number. There's no half of a proton or half of a neutron, right? It's either there or it's not. So our mass number is always a whole number. Okay, so if we look at one of the images, if we look at the first one that has 2 protons and 2 electrons, that is helium. Because it's number 2, it's got 2 protons, it's number 2, so it's the second element, it's helium. And it's neutral, so 2 protons means it has 2 electrons to stay neutral. On the other one, what atom is that? Oh, it says on there. We can count the number of protons in the nucleus. It is 6. That means it's a carbon atom. Now in that case, yeah. So neutrons have a similar mass to protons, and different individual atoms can have different numbers of neutrons in the nucleus. And that means that there are different atoms that can have different weights. So maybe this is like twins. Maybe you know some triplets, and there's three siblings, and one of them is just a bit heavier, right? That's all it is. That individual atom has extra neutrons, and it has a slightly higher mass because it has an extra neutron. So when we look at this atom, oh, here we go. What atom is this one? We can count the protons. The protons are red. In each case, these both have 6 protons, which means that it's a carbon. In the top one, oh, and you can also notice they each have 6 electrons, so we're still looking at neutral atoms. In the top one, it has 6 gray. Those are the neutrons. In the bottom one, it has 7 gray balls, 7 neutrons in there. So the first one on the top is a carbon 12, has a mass of 12, and the next one has a mass of 13. These are 2 different individual atoms that have a slightly different mass. These are called isotopes. Isotopes are individual atoms. And then for that individual atom, we can talk about what is the mass of that individual. So isotopes are just different individual particles of a given element. They can have different masses. So we use an isotope symbol to clarify how many neutrons it has by giving the total mass. Now, it turns out when we look at elements, we talked earlier about the natural abundance of elements, how the Earth's crust is mostly oxygen. When we take a sample of the natural abundance of an element, we will have some that have, like there will be some carbon 12, and then some small amount of them will be carbon 13. And that natural abundance, we take the average, because if we take a sample, if we scoop up a sample of an element, we have a lot of particles. And so that's going to represent the percentage of the main element plus the percentage of whatever those other isotopes are. So we're going to take a weighted average of all of those individuals. So let's take a look at that. Here is here's hydrogen, right? These all have 1 proton. So these are all isotopes of hydrogen. Now, normal hydrogen, if you look on the chart, it has a mass of 1. So normal hydrogen has 1 proton and no neutrons. If we have a hydrogen that has a neutron in the nucleus, that has a mass of 2. And it gets a special name, right? That's deuterium. And it's often a byproduct of nuclear reactors, for example. If we have a hydrogen that has 2 neutrons, then it is a tritium. So it's just it gets its own name. And it's also a byproduct of nuclear reactors. They all have 1 proton, they all have 1 electron to stay neutral. 1 proton, they're all hydrogen. But deuterium and tritium have extra neutrons. They just have a slightly higher mass. So these are isotopes of hydrogen. We can also look at neon. 90% of neon has 10 neutrons in the nucleus. There's a very small amount of naturally occurring neon that has 11 neutrons, and about 9% of neon has 12 neutrons. So when we look on the periodic table, we have a mass of 20.18. That's the average of all of this natural abundance. So 90% of the mass 20, and a pretty good contribution of mass 22, and a very tiny amount of neon has mass 21. When they're all added together, the total is 20.18 is the average of a huge collection of naturally occurring neon. So when we talk about isotopes, this symbol here, that's 1 individual. And when we talk about the mass on here, that's the average in a sample that you might get, right? Because you're not going to just take 1 atom typically. Take some specialized equipment to look at 1 atom by itself. So we're going to introduce the symbol for isotopes. That has the element symbol, in this case hydrogen. Up on the top, we have the mass number. So that's always the protons plus the neutrons in that individual particle, just that 1 atom. And then the atomic number gives us the number of protons. But that is duplicate information. It's the same thing as the symbol. If it's a hydrogen, it's number 1. If it has 1 proton, it's a hydrogen. So if I go back for a second and look at this one, you see when I say neon 20, that's all the information. In the official symbol, we have the neon and we have the number 10 because neon is number 10. So the 10 is the same information. It's the 20 that's going to give us the total mass. And because of that total mass, it's going to give us the number of neutrons in the nucleus for that individual atom. So here's a couple examples. Here I have E as general as the element symbol. If it's a 2-letter symbol, remember the first one's capital, the second one's lowercase. And then the mass number is up on the top and the protons are down at the bottom. So on the carbon, they both are number 6 because they're carbon, but one has 2 extra neutrons. So it has 6 protons plus 8 neutrons to get a carbon 14. So we'll use those in our worksheets. We're going to pick up with the worksheets. We'll talk more about weighted averages tomorrow too.
So for example, if we look at gold, right, AU, and it says the mass is 196.97. It's the mass of both protons and neutrons. And then it says 79, the number 79. What does 79 stand for?
79 protons.
Okay, so then to find out how many neutrons, all we need to do is just subtract from the total mass?
Kind of, because there's no half of a neutron or half of a proton. This value here is an average. So we would have to say, okay, which individual? If we're going to talk about one individual, which one is it? Maybe I'm talking about gold with a mass of 198. That could be the dominant isotope. I'm not sure. I don't know for sure. But maybe that's the main one. Now, if that is the main one, then we would have 198 minus, so this is protons plus neutrons. And then we're going to take away minus 79 protons. So that's how we're going to calculate the number of neutrons.
Okay.
Not tomorrow, we're going to talk a little bit more about the average and how the average differs from the individual atoms. And then we're going to look at calculating the number of neutrons.